Hi, everyone. Well, I'm very excited to talk with you today about ground-based and space-based high contrast imaging. And my goal for today is sort of to try and bridge a lot of the topics that we've encountered this week in these amazing talks and some of the poster presentations that are here at this conference, to sort of bring the technical and the observational and the scientific sides all kind of together. And then I'll try to do sort of a whirlwind tour of what we've learned in the last 2 years from JWST. So I want to start with a few motivating questions for why we want to compare and contrast ground-based and space-based imaging. So the first question we should ask ourselves is, what do we achieve by going to space anyway? We know we can build much, much larger telescopes here on Earth. And what are the trade-offs between observing from the ground and from space? And that's a question you might get a lot as we enter the age of the ELTs. How do JWST and HST and Roman fit into this picture? What are some of the lessons that we've learned through our history of ground-based high contrast and adaptive optics imaging? What are we learning right now? Mostly I'm going to focus on JWST, but I'll just remind you that we still have chronographs that are operational in HST as well. And what does this mean sort of into the future for this era where we will have ideally JWST for the next 20 years or so, as well as ground-based ELTs that are operational? Throughout the talk, I'm going to highlight some relevant poster numbers that are related to the topics that I'll cover. So I encourage you to find these authors and talk to them specifically about sort of JWST chronography. Okay, so I want to start by reminding us that we are on the 30-year anniversary of directly imaging the first substellar companion to a star. And so this is an image of the brown dwarf GL229b, a cold T-dwarf methane-rich companion that was discovered in October of 1994. And one thing I really like about this is that we're looking at two images side by side. The one on the left is from the Palma 1.5 meter telescope that had an AO system, early AO system from JHU, and a chronograph, even though that might be hard to believe based on the scattered light that we have here. And then the other image on the right is from the WIF-PIC2 camera on HST. It's a non-chronographic image, but you can sort of see the clear detection of our T-dwarf companion here. So we have a sort of rich history that we're building on as we move to higher contrast from the ground and from space. So I want to start by talking a little bit about the similarities from kind of all of the technical talks that we've heard this week between ground-based high contrast imaging and space-based high contrast imaging, and a few of the differences that we should keep in mind as we sort of launch into this era. So the first similarity that I'll mention is that we need to have a careful understanding of the PSF for robust starlight subtraction, and also to be able to forward model the PSF of our companion of interest and extended sources like disks. We need to understand the optical properties of the telescope really well. And actually, all of you have done this from the first day on the first hands-on session by simulating what we know a ground-based PSF should look like from first principles, and also what a complex multi-segmented telescope PSF should look like as well, not including the many aberrations that we have to consider in this regime. But we need to understand these as well as we can from an optical design principle to be able to characterize our instruments. The other thing we care about from both the ground and from space is wavefront error. And so wavefront error is super important for both regimes, but I will say that they're on pretty different temporal and dynamic range scales. So this is a very cute cartoon of everything we've been talking about this week from the ground. When we have an AO system on the ground, we have this nice ideally unaberrated wavefront that's coming in, hitting atmospheric turbulence. We've heard from just in Julien's talk that there's all of these considerations that we have with the different layers of turbulence and how they aberrate our PSF. We then can introduce our control loop here to measure the wavefront and send that back to the deformable mirror. And ideally, we get a nice, sharp, high Strel PSF on our detector. And to give you sort of a sense of scale, when we talk about wavefront error, we're measuring it in nanometers. So we're talking about the deviations from that plane parallel wavefront on the orders of hundreds of nanometers. If we think back to the Keck AO system kind of early in the early 2000s, we're thinking about RMS wavefront error on the order of 180 to 250 nanometers. And those are numbers to keep in mind as we start to talk about what we're doing from space. But the other thing that we should remember is that these changes, as we just saw in Julien's talk, are happening very, very fast, right? We have to sort of compensate and keep up with these rapid changes in the atmosphere. Now, how does this compare to space? So here are some optical path difference maps for JWST taken last October. And here we're seeing a wavefront error that's sort of on the order of about 60 nanometers RMS. And this is stable on the order of days. These are multiple separate days of observation on JWST. I will do a pop quiz real quick and ask if anyone knows what's going on in this segment right here, where the range and the wavefront error is quite large. You can just shout it out. Something hit it. So if you remember, very soon after JWST launched and arrived on orbit, there were some micrometeorite impacts. This is that residual largest event just shortly, I think during the commissioning phase, which is introducing some residual wavefront error that is just there we have to contend with. So this is stable on the order of days. So this is a very different sort of frequency space that we're thinking about. But I will say that even though JWST is in space, we have these minor incidents and impacts that are not unexpected from being kind of open to the ambient environment of space. The telescope does not just stay at this wavefront error all the time. And so just a few days later, we have what we call a tilt event. And so you can see on just this segment here, we see a huge sort of like tilt of that segment that leads to closer to 100 nanometers of wavefront error. So there are dynamic changes in the wavefront we have to consider when we're thinking about our PSFs. The other thing I want to sort of bring together is that we have this kind of rich heritage of PSF subtraction. We heard in Faustine's talk all of these different methods of PSF subtraction, and in particular things like angular differential imaging. We have a rich heritage of this that actually starts with HST. So angular differential imaging was sort of introduced in this idea that Hubble has this nice, ability to roll along its long axis, which gives us this angular diversity. And there's this then realization that we could just apply that to large ground-based observatories where the PSF sort of stays the same and your astrophysical source rotates around it. And to give you a sense of sort of what that looks like in this little cartoon animation of the Orion constellation rising and setting, if we turn off our image rotator, which is sort of the equivalent of what you're seeing in that red box there, then we will see sort of everything astrophysically just rotate as the sky rises and sets. And so it's the same exact principle that we do in space by rotating all of Hubble versus turning off the image rotator on the ground. And what this looks like in practice then is that you have this series of images. You have your astrophysical source that is rotating through your image in this long sequence, but your PSFs should stay relatively the same. You then median combine them to reject the astrophysical source of interest, leave just the stellar PSF and subtract it. And I would encourage all of you, if you haven't seen it yet, there's a really nice high contrast imaging review by Kate Follett published last year that sort of bridges a lot of the things we've talked about this week together. So that's ADI, as you've learned. But as we've talked about a lot this week, we can also use large image libraries to generate appropriate PSFs, or even just choose one really good star to be our reference image to subtract off as well. And so this reference differential imaging has a lot of considerations, and some of the ones that are important for us to think about as we go to space are, do we pick the one singular perfect reference star that is the exact replica of our science target and try to subtract that off? Does such a star even exist? Sometimes it doesn't. And can we leverage like large libraries of reference stars to try to combine them in a PCA-based analysis and kind of build up what we think is the closest match PSF to our science target? Something that we've learned from Hubble, and we are learning rapidly with JWST, is that we got to match things perfectly. So we need to match the stellar flux of your reference star, which should be a boring star with nothing astrophysically interesting about it. But we also need to match spectral type and color. JWST has these effects like a brighter, fatter effect, where in the mid-infrared, the PSF grows as you shine more light on the detector. That's problematic if your star doesn't match your science target perfectly. So we have to kind of keep all of these things in mind. And there are a couple great posters talking about these techniques that I encourage you to look at and talk to Sandrine and Mathilde. Okay, I'm just going to highlight some of the major differences in kind of one slide. The first of which is, in space, we're quite lucky that the PSF structure and evolution with time is much more well behaved. The stability is just much easier to characterize. And the pointing is very, very good, and the repeatability is very, very good as we slew JWST, HST around. So for example, we can point the telescope for JWST to about 5 to 10 milliarc seconds pointing accuracy, which is quite good for putting your star of interest behind your chronograph. The jitter, sort of small variations in that position of the star, is often less than 2 milliarc seconds. So it's very, very stable compared to what we have to contend with from the ground. There's a downside, of course, that space telescopes are smaller, and that means our lambda over d is much larger for a smaller diameter telescope, which means we have much larger inner working angles on the order of about 0.3 arc seconds for both MIRCAM and MIRI. And whereas from the ground, we routinely have inner working angles that are better than 0.1 arc seconds. There's a kind of a fun thing for JWST, which is slightly problematic, which is if you want to do ADI and roll your telescope around, you really can't very much. And that's because of the sun shield configuration of JWST, you can only sort of roll it from 5 degrees to 14 degrees maximum from side to side, which is hard if you want like that nice diversity of angles to make your reference star. And I don't have a ton of time to talk about it, but there's also these other considerations that we didn't know about until launch, which was there are glow stick effects, which you can ask me more about. And we also realized we need dedicated backgrounds in the infrared to be able to sort of reduce our data and get the best contrast possible. The upside of that is that from space, we have access to wavelengths we just can't access from the ground at all. And that's opening up new science paradigms. And there's a much lower thermal background. And as you saw from Rob's talk, earlier this week, that as you go past 2 microns from the ground, it just gets real dicey to try and do thermal infrared imaging. And so we're really winning out in sensitivity and contrast with JWST. I also want to remind us that it's not really a big telescope. And so this is JWST shown to scale images courtesy of Marshall Perrin to Keck and to VLT. I'll just let you imagine in your mind's eye for a moment. There's TMT, what we have on the horizon. And even though JWST is not that large, it has all these features that are great for high contrast imaging. It's exquisitely stable. We don't have to think about atmospheric wind turbulence effects or telluric absorption features that like block out whole ranges of the EM spectrum. And I would be remiss if I didn't include HST with a school bus to scale for a comparison. Okay. So I'm not going to spend a lot of time talking about this because it's been covered in exquisite detail from talks by Becky and Sebastian and Julien. But there are aberrations in space that we have to think about. The major ones are these slow evolution of thermal mechanical effects, like that tilt event that you just saw in the JWST optical path difference map. One of them that's been very well understood is that HST, for example, as it's orbiting around the Earth, the telescope structure breathes as it has different temperature regimes that sort of illuminate it and heat it. That changes the PSF pretty dramatically, which you have to consider when you're subtracting it off. JWST has these tilt events that we saw that is actually just, some of them are just due to relaxation of the telescope structure itself and sort of a stick-slip motion of the segments. And one thing that's kind of cool, and I'll show you in a second, is that JWST does not have AO, right? It doesn't have like a sort of adaptive control loop that's being applied, but it does have an active wavefront sensing and control system that corrects every so often. So what does that mean when we think about stability? So this is a plot of the first year of JWST observations in cycle 1. And what we're looking at here is the wavefront error in nanometers on the y-axis. Whoops. There we go, on the y-axis. And so you can kind of see this sort of nominal 60 nanometers of wavefront error as a function of time over the course of a year. And you see each of these dots as a measurement of the wavefront error on flight. And you'll see that every so often there are these big excursions to higher values that then we can correct by introducing some active optics to kind of push the segments back into place and get a nice cleaner PSF. But that means if your favorite science target where you're trying to find your favorite directly imaged planet was taken right here, you need to find a PSF that will match in time because it will be significantly distorted. The good news is that the typical change in wavefront over the course of days, over 2 days, is about 10 nanometers or less than 10 nanometers of change. It's pretty great. That's good news for us in terms of using a library of old PSF observations that maybe were taken like a year or 2 before your observations and try to use those to subtract the starlight from your images. Okay, so what are we contending with when we want to do high contrast imaging with JWST? Specifically, I'm going to kind of focus of the entire suite of instruments with JWST on what we do with chronography. So we have the near-cam chronographs, which are 5 band-limited LEO chronographs from about 2 to 5 microns. And then we have the MIRI chronographs, which feature 3 4-quadrant phase mask architectures and a LEO chronograph. Covering 10 to 23. I'll also briefly mention that there's some very cool high contrast spectroscopy that we can do as well. Okay, so what are the zoo of chronographs that we have to that we get to use in space right now? So the first one is the on HST. It's actually the oldest operational instrument on HST is STIS, and it has this suite of wedge chronographs. So each of these little plus signs you can place your star behind and block more and more of the PSF. We also have a couple bars, including this very silly, tiny little bar that was bent in flight in 1997 when things were implemented on HST. You can put a star behind that and get very close inner working angle in the optical, which is pretty great. And the only way we can really do that at the moment. I will just point you back to John Davis's talk on Tuesday about debris disk, that this is literally the least optimized chronograph in space, but it still works and you should still use it. Then there's also, for JWST, we have the near-cam chronographs. So we have these LEO chronographs that are circular round masks, as well as these wedge chronographs that are very similar to what we saw sort of with HST here that have varying widths. And then with MIRI, we have something kind of interesting in that we have sort of a more classic LEO chronograph at the longest wavelengths. But then we have these 3 detectors with these funny little plus shape symbols, these 4-quadrant phase masks, where you put the star directly behind these very thin, very fine sort of cross symbol shapes. And you allow destructive interference with the different phase offsets between the 4-quadrant phase masks to suppress starlight. And if you want to learn more about these, there's some great posters on the NearCam side from William and Rodrigo, and then there's some great posters on the MIRI side of chronography from Mathilde and Aniket. So how do we subtract starlight from JWST? This is kind of the last thing I'll talk about before we kind of move on to the science. So the first thing you want to think about is when we move JWST to our star of interest, hopefully it has a planet around it, we have to place the star behind the chronograph, and we don't know exactly where it goes. So especially for those round masks, if you put the star behind it, we know JWST's pointing is very good, but we don't know exactly where it's landed. And one of the ways we get around this is when we take our reference star observations, we actually move the reference star around. We use the fine steering mirror on JWST to add little jiggle offsets to the position of the reference star behind the mask. You'll notice that this plot is basically on tens of million arcsecond scales to sort of move that reference star. And the hope is one or more of those images from your reference star will match wherever the star of interest landed behind the chronograph for your science case. Once we do that, then we can apply a suite of RDI, ADI, we can combine RDI and ADI, and we can determine what the achievable contrast looks like. So here are some 5 sigma contrast curves from the early release science program by Aaron Carter. We can see the contrast as a function of separation here for NearCam at 4 microns and for MIRI at 11 microns. And what you see, you can kind of just focus on the black curves here is the difference between ADI, RDI, or combining both techniques. And there are regimes where RDI outperforms a little bit, and there are regimes where the combination outperforms a little bit, and you have to think a bit about your science case where your object of interest is to get the best achievable contrast. Once you want to do that, then you can apply space clip, which is all of you are doing a clip on Tuesday. So PyClip implementation for JWST, which kind of combines with JWST pre-processing, is kind of all packaged together and very nicely documented. And I encourage you to try that out. And there's also a very nice comparison of ADI and RDI methods in Sandrine's poster. One thing I will mention that I don't really have time to talk about is because we can model the PSF really well, we can actually just make a synthetic PSF. There's a possibility that we're still trying to figure out that we might not actually need a reference star at all. Can't quite do that yet. We still need reference stars. But if we could know the optical system really well in principle, we could use those OPD maps and build our custom tailored perfect PSF. We're trying to do that. It's hard. Okay, science. So what are we doing right now and what's coming next? So I had to update my slides yesterday because yesterday morning a new Nature paper dropped, and we saw it a little bit earlier this morning as well. The Epsilon NDB is now the coldest, oldest directly imaged exoplanet, and it's actually quite surprising as well. So as you heard earlier, this is a solar type star of about solar age. It has this wealth of information that you've seen in our previous talks. They're kind of leading us toward taking our RV trends and Hipparcus Gaia accelerations and using that to try and find new planets. And so they did this. So Elizabeth Matthews and collaborators used the MIRI chronographs at 10 and 11 microns and found this exceedingly bright point source in these 2 images here. And this detection is consistent with that, as we saw earlier, a very cold sort of 6 to 8 Jupiter mass planet. But what's very curious about it is from the astrometric orbital solution and the RV trend, they're actually expected to see it down here. So it popped up in the wrong quadrant. which is interesting. But they went back to VLT archival data, and we're actually able to reprocess that data and dig it out of the signal to noise of 3. And sort of those 2 astrometric points you see in their orbit fit here are from that archival data plus the new JWST data, and there are orbital solutions that are consistent with that. And this long-term, you can see it's almost 40 years of RV coverage that allow us to constrain the properties of this planet. They also were able to go back to Spitzer and see that there were non-detections in Spitzer. It's actually very interesting because that means at 3 and 4 microns, there's no flux. And that if you try to fit models to that, it suggests that we're dealing kind of with this unusual planet, this very high metallicity, potentially a very high C to O ratio. So a composition that's also sort of surprising at this very cold temperature. One of the first planets that was directly imaged with JWST, as many of you have likely seen, is HIP 65426, one of the discoveries from SPHERE. And you can see this is a nice example of how inner working angle is different from the ground and from space. So here you see the discovery image of the planet. Here are the 5 round mask NIRCam detections. And here are the first 2 ever thermal infrared images of an exoplanet beyond 10 microns. And so one thing that is very cool is that we can start to build all of this spectrum together, right? We can start to combine what we're learning from JWST way out here in the infrared with everything we've learned from the ground and fit models. And what we're learning is modeling atmospheres is difficult, as we talked about extensively this week. But also we are starting to constrain the bolometric luminosity and the radii of these planets by being able to get basically all of the emergent flux from them. So that's quite exciting. And there's also really exciting work, as you saw from the spectrum with MIRI, of image companions with ERS. We've also talked a lot about AFLEP-B, so I won't spend a lot of time talking about this, but this is still to date, the closest separation image planet with JWST. And this is, again, a very nice proof of concept that shows us that if we can use all the information to our advantage before we image the system, we can basically make rejection sampling maps that take our position angle and our separation and determine exactly where we would expect to see the planet. But here you can also see that there's some degeneracies in the solution, and maybe that's what happened with Epsilon Indy. Why it showed up somewhere where we didn't expect it. And I believe Kyle is here and has a poster, so definitely talk to him about these astrometric beacons. I'll also talk briefly about this benchmark ground dwarf that was imaged with JWST. So this is another system for which there was extensive RV monitoring that suggested the presence of a giant companion. It was imaged with NIRCam here. And then as you saw this actually in JB Rufio's talk earlier this week, this is an exquisite system where you can get very nice signal to noise in IFU spectroscopy. And one thing that's really cool here, there are actually 2 really cool things about this NIRCam image, one of which is that they use a synthetic PSF, basically a totally artificial model PSF to subtract, and it worked pretty decently. The other thing is that when they extracted the spectrum of this planet, the photometry was consistent with the IFU spectra, which is great. That's a nice confirmation across different instruments that we're getting kind of the same fluxes. And so the fact that we can start to get 3 to 5 micron RV2700 spectra on image companions that are very faint, kind of approaching these 10 to the minus 5, 10 to the minus 6 contrast levels is pretty spectacular and something we're very excited about as we move forward with high contrast spectroscopy with JWST. There's also one of our favorites that you've seen many times this week, HRA 799. This is what it looks like in the mid-infrared. So you've seen the beautiful orbiting planet movies. Here, of course, we're at much longer wavelength. You can see from the MIRI coronagraphs at 10, 11, and 15 microns, and then a non-chronographic image at 21 microns. All 4 planets are detected, which is great. And fun bonus, which is a real problem that we're encountering as JWST is so sensitive. There's lots of point sources that look like promising, exciting dots that we're learning are likely Z of 1 plus background galaxies. And here's an example of one that they were like, oh, is this maybe F, HRA799F? And no. But one thing that you can also do here is this is the first sort of image of the inner warm debris disk of the system seen for the first time. Some of the things that we're learning from the mid-infrared is that as we include that mid-infrared photometry, we're basically starting to be able to constrain the radii and temperatures, and we're getting slightly different answers than what we did with just the near-infrared before. So there's some interesting physics here. Either it's just discrepancies in the data, potentially some model limitations in our atmospheres and chemistry, but they're things we have to think about. And I encourage you to stay tuned for some near-term observations. We'll fill in wavelength coverage that we weren't able to do from the ground by William Balmer, who has a nice poster on the system as well. One thing that is sort of up and coming that we can also get excited about, just as we saw from JB's talk about IFU spectroscopy in the near infrared, is that MIRI MRS allows us to do IFU spectroscopy from 5 to 20 microns as well. And so this is a simulation of, again, what the HRA79 system could look like with MIRI MRS in terms of how we're able to cross-correlate the atmospheric signatures of the planet, but now at a much longer wavelength regime. So this should be an area that we can capitalize on within the next few years as well. And I will remind you that there's a lot of molecules we just can't do from the ground. And even in places that we can do from the ground, like at 4.6 microns, the Earth's atmospheric transmission is like less than 30%. So it's hard. It's really hard to do. And so we can still win out sensitivity-wise. I'm going to talk briefly about the disks too. We had some questions about disks as well. So here's one of our famous debris disk systems, Fomalhaut, as imaged for the first time in the mid-infrared with JWST with the 4-quadrant phase mask at 15 microns, the classical Leo, and then an unocculted image at 25 microns. And one of the things we're learning here is we can start to compare these sorts of disk architecture systems from the visible light with HST STIS at 0.5 microns to what we're learning from MIRI and all the different components of the hot inner disk, the gaps, this is basically the first ever resolved asteroid belt, and then finally an almost a millimeter detection as well. Yeah. Yeah, okay, yeah. And I want to say that there's deep searches for planets in these systems, and it's chaotic, and they're all background sources, and we have to figure out what they are. One of them might be promising. The last couple of this, I'll talk about Beta Pictoris, the most famous first resolved debris disk system. If you zoom in, you can actually get both the disk and the planet at the same time with NIRCam. And we're finding it's really hard to image both the disk and the planet and measure them separately at the same time. So that's a problem for all of you to start to work on. And we're learning that this is also an issue as you go out to the mid-infrared. And we're seeing that there's actually, these are all to scale from 2 microns to 23 microns. And you can see that the disk glows in very different ways. And there's actually substructure that we didn't expect that has been affectionately referred to as the cat's tail, as you see this like little blip here, that appears to be a dynamically driven feature in the disk. And I also point you to other really cool disk systems like HD 95086, where we can resolve the inner disk, see the planet, and also see the outer disk as well. This is a laundry list that I'm happy to talk about of all of the really exciting science that's about to come out. Dynamical masses, protoplanets, atmospheres, sub-Saturn mass planets. Some of the PIs are in this room, so I encourage you to talk to them. And then we heard a lot about the new upcoming surveys. There's lots in cycle 2 and 3 to get excited about. And I'll skip this just because this is a bridge to tomorrow, but you're going to hear all about the ELTs and what we can do with them. But I'm happy to answer questions about the synergies. Here's some of the takeaways. We talked about the similarities and differences. JWST is not large, but sensitivity is really key. We have lots of disentangle in these disk structures at this new sensitivity. And there's a lot of exciting discovery space. And I'll just implore you to not forget to use HST while we still have it. Thank you.
Yes, sorry for putting pressures on you. At the end, it was a very nice talk. We have time for one question before we get to lunch break. And before the hands-on session this afternoon for the projects. Also, feel free to talk with Kim during the rest of the Sagan workshop. So I guess there's no questions.